Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Imagine waking up one morning to discover that Earth is no longer where it used to be in the solar system. The sun looks a little smaller, or perhaps it's glaring a little brighter. Seasons feel strange, weather patterns shift dramatically, and the familiar rhythms of day and night start to feel alien. The thought of Earth being in a different orbit might sound like science fiction, but the consequences of such a cosmic change are both fascinating and terrifying. Our planet's orbit is a delicate dance, perfectly tuned over billions of years to sustain life. But what if this dance were altered? What if Earth revolved closer to the sun, or farther away, or even in an entirely different path through space? The very nature of life, the climate, and the evolution of ecosystems could be rewritten in unimaginable ways. Earth orbits the sun at an average distance of about 93 million miles, a sweet spot astronomers call the habitable zone. This zone is not too hot and not too cold, allowing liquid water to exist, water being essential for all known forms of life. If Earth were nudged inward toward the sun, the first noticeable change would be a dramatic rise in temperature. The ice caps would start melting rapidly, oceans might expand, and desertification could sweep across continents. Crops and natural ecosystems adapted to moderate temperatures would struggle to survive, and some regions could become uninhabitable. A planet closer to the sun would also receive more solar radiation, increasing the risks of heat waves and intense storms fueled by the extra energy. In such a scenario, humans might be forced to migrate toward cooler regions or develop technological solutions to shield themselves from the sun's wrath. Conversely, if Earth drifted outward, away from the sun, the planet would enter a chilling regime. The amount of sunlight reaching the surface would decrease, and global temperatures could plummet. Winters would grow longer and harsher, summers might barely thaw frozen landscapes, and many regions could be locked in perpetual frost. Oceans could freeze over at higher latitudes, disrupting marine life and global weather systems. Agriculture would suffer, and human civilizations would have to adapt to extreme cold. Survival might depend heavily on energy and infrastructure designed to resist the creeping freeze. Interestingly, life might persist underground or near geothermal hotspots, but the surface of Earth could resemble a frigid, inhospitable world. Beyond the mere warmth or cold, the shift in orbit would dramatically affect the length of the year and the progression of seasons. Currently, Earth takes 365.25 days to complete a circuit around the sun, a rhythm that underpins calendars, agriculture, and biological cycles. Move Earth closer, and the orbit speeds up, shortening the year. Move it farther, and the year stretches longer. Animals and plants that rely on precise seasonal cues might find their reproductive cycles thrown into chaos. Migratory birds could arrive too early or too late, disrupting food chains. Flowering plants could bloom out of sync with pollinators, triggering cascading effects across ecosystems. The subtle timing that life has evolved with could be fundamentally broken. The tilt of Earth's axis combined with its orbital path produces the seasons as we know them. But if the orbit changes drastically, the relationship between the tilt and solar exposure could alter in surprising ways. Regions that once enjoyed mild summers and winters might face extreme climates. The tropics could expand or shrink, polar ice might melt or grow unpredictably, and monsoon patterns could shift, affecting billions of people who depend on predictable rainfall. Even ocean currents, driven by temperature differences and wind patterns, could be disrupted. A new orbit could transform warm currents into icy flows, or cold currents into unusually warm ones, reshaping climate zones and impacting marine ecosystems that are finely tuned to specific temperature ranges. Gravitational effects would also play a critical role in a new orbit. Earth's orbit is not just about the sun, it is influenced by the gravitational pull of other planets, especially gas giants like Jupiter and Saturn. If Earth moved closer or farther, these interactions could become more pronounced. Jupiter's gravity might tug Earth into a more elliptical orbit, causing extreme variations in distance from the sun during the year. Such fluctuations could bring scorching heat followed by intense cold within months, creating climates far harsher than anything experienced in the current geological record. Long-term stability of the orbit would be in question. Over centuries or millennia, even small gravitational nudges could accumulate, potentially ejecting Earth from its orbit entirely or sending it into chaotic patterns. Another fascinating aspect of changing Earth's orbit is the effect on the day-night cycle. While orbit primarily determines the year, it also subtly influences the length of days through tidal interactions with the moon and sun. A closer orbit could increase solar tides and slightly affect the speed of rotation, while a more distant orbit might alter the gravitational relationship with the moon, affecting tides and perhaps even the stability of the planet's rotation over long timescales. These changes could influence everything from ocean currents to the behavior of nocturnal animals and even human sleep patterns. A different orbit could also expose Earth to new hazards from space. Our planet's current path shields us from many comets and asteroids by virtue of Jupiter's gravitational influence and the layout of the solar system. A new orbit might place Earth on a collision course with the more space debris or bring it closer to regions where comets and asteroids are more densely populated. The history of life on Earth is punctuated by catastrophic impacts, and a shift in orbit could increase the likelihood of these devastating events. Over millions of years, this could profoundly influence evolution, potentially wiping out dominant species repeatedly or allowing entirely new forms of life to flourish. In imagining Earth in a dramatically different orbit, it's impossible to ignore the effects on human civilization. Agriculture, energy systems, infrastructure, and urban planning are all designed with current climate and seasonal patterns in mind. A hotter Earth could make large swaths of land uninhabitable, driving mass migrations and conflicts over remaining habitable regions. A colder Earth could freeze agricultural productivity, forcing humanity to rely heavily on artificial environments for survival. Sea level changes, either from melting ice or freezing oceans, would reshape coastlines and urban centers. Cities could vanish underwater or become frozen wastelands. Humanity's technological and social adaptability would be tested like never before. Yet, this thought experiment also sparks fascinating scientific speculation. Could life have evolved differently if Earth had been in a slightly different orbit from the beginning? Perhaps tropical species would dominate the poles, or perhaps polar-adapted life could thrive near the equator. Could intelligent life emerge in harsher, colder conditions, relying more on technology and ingenuity to survive? Such scenarios push the imagination and remind us of the delicate balance that allows our planet to host life. Earth's current orbit is not an accident. It is a product of cosmic conditions that, by chance or necessity, favored life as we know it. Beyond biological and climate considerations, moving Earth to a different orbit would alter our view of the solar system. The apparent size and brightness of the sun would change, and the positions of planets in the night sky would shift. The constellations themselves would remain largely the same due to their vast distances, but planets would traverse unfamiliar paths across the heavens. This could affect astronomy, navigation, and even cultural interpretations of the cosmos. For civilizations that have looked to the stars for millennia, a change in the sky could feel like the world itself had been rearranged. The psychological and philosophical implications are also intriguing. Humans often take the consistency of seasons and the predictability of climate for granted. A change in orbit would remind us of our planet's fragility and the delicate conditions that sustain life. It might inspire a new appreciation for the interconnectedness of all planetary systems and the precariousness of existence in the cosmos. Science fiction often explores such scenarios, but contemplating them through the lens of science reveals just how finely tuned our world is for the life it supports. Interestingly, even minor adjustments in orbit could have long-term consequences over geological timescales. Milankovitch cycles, which are natural variations in Earth's orbit and axial tilt, already drive ice ages and warm periods. Altering Earth's orbit significantly could amplify or suppress these cycles, creating climates far outside the range humans have ever experienced. Glacial periods could last tens of thousands of years longer or shorter, and interglacial warm periods could be drastically hotter or colder. Evolution, biodiversity, and human history would all be reshaped by these planetary rhythms. The composition of the atmosphere could also respond to a different orbit. Increased temperatures might accelerate the release of greenhouse gases from permafrost or oceans, creating feedback loops that intensify warming. Conversely, a colder orbit could trap gases in frozen reservoirs, thinning the atmosphere and reducing its ability to retain heat. Clouds, precipitation patterns, and storms would all adjust to the new energy balance. A shift in orbit could transform the planet's weather system so dramatically that familiar climate zones disappear entirely, replaced by new, unpredictable regimes. Even Earth's magnetic field, though primarily generated by the core, could experience indirect effects. A shift in orbit could influence the flow of solar wind across the planet, potentially affecting the magnetosphere's interaction with charged particles. Increased solar radiation at a closer orbit could test the limits of this protective shield, while a more distant orbit might reduce the intensity of auroras, but could also alter radiation exposure for satellites and astronauts. Human technology, dependent on electronics and satellites, could face unprecedented challenges in adapting to these cosmic changes. One cannot overlook the effect on water cycles. A warmer Earth near the sun might see faster evaporation rates, altered rainfall distribution, and more intense storms, while a colder Earth could experience diminished evaporation, snowfall accumulation, and frozen rivers and lakes. The delicate balance that maintains rivers, lakes, and aquifers could be disrupted, threatening both ecosystems and human settlements. Agriculture, freshwater access, and biodiversity would all feel the consequences of a planet out of its familiar orbit. Ultimately, imagining Earth in a different orbit illuminates the incredible precision of our cosmic circumstances. Life, climate, seasons, and human civilization are intertwined with the planet's exact distance from the sun and its stable path through space. Even small changes can ripple through ecosystems, weather patterns, and the very survival of species. Yet, this thought experiment is not merely a cautionary tale. It is an invitation to marvel at the delicate choreography of the solar system, to appreciate the cosmic conditions that have allowed life to flourish, and to imagine how different the world might have been under other celestial arrangements. Our planet's orbit is more than just a path through space. It is a guardian of life, a sculptor of seasons, and a stabilizer of climates. It enables the oceans to remain liquid, the poles to host ice, and ecosystems to evolve in harmony with predictable cycles. To imagine Earth elsewhere is to confront the profound fragility and resilience of life itself. It reminds us that we inhabit a universe of precise balances, where even the smallest deviation in a planet's journey around its star could redefine everything we know. In the end, pondering what if Earth was in another orbit is a meditation on chance, balance, and the extraordinary fortune of life on a planet so perfectly placed. Imagine Earth pushed dramatically closer to the sun, skimming the inner edges of the habitable zone, or even venturing into regions like Venus's orbit. The sun would dominate the sky, blindingly bright and enormous, casting relentless heat across every continent. Equatorial regions might resemble the surface of a furnace, with temperatures high enough to melt asphalt and bake soil into hard, cracked plates. The polar ice caps could vanish entirely within decades, flooding coastlines as sea levels rise rapidly. Even the atmosphere would change under such conditions. Water vapor, acting as a greenhouse gas, could trap heat and intensify global warming, creating a runaway effect akin to Venus itself. Hailstorms and hurricanes might become unimaginable in intensity, fueled by the extreme heat contrast between tropical and higher latitude regions. Life would need to adapt or die. Survival for humans and animals in such a scenario would demand extraordinary technological intervention. Cities might be covered in reflective domes to shield from solar radiation. Underground or underwater settlements could become commonplace, insulated from the burning surface. Agriculture could shift entirely to controlled indoor environments with artificial sunlight and temperature regulation. Energy demands would skyrocket as humans struggled to maintain habitable conditions. Yet, even with technology, the challenge of sustaining life on a scorching Earth would be unprecedented, potentially limiting human habitation to specific high-altitude regions or artificially cooled zones. Conversely, moving Earth outward, past the current orbit into realms closer to Mars or the asteroid belt, would plunge the planet into frigid darkness. Average global temperatures could drop well below freezing, turning oceans near the equator into icy expanses and extending glaciers toward the tropics. Food production would become almost impossible on open land, forcing humanity to rely entirely on indoor agriculture, hydroponics, or genetically engineered cold-tolerant crops. The air might thin slightly over millennia as colder temperatures affect the distribution of gases, and the energy budget of the planet would shift toward heat retention rather than radiation dispersal. Even survival for many animals would require adaptation or migration, and many species could face extinction due to the sudden extreme cold. The length of the year in such scenarios would be profoundly altered. A faster orbit closer to the sun could shrink the year to 200 to 300 days, compressing seasonal cycles. This acceleration would disrupt breeding cycles, hibernation periods, and agricultural schedules. Conversely, a distant orbit might stretch the year to 500 to 600 days, elongating seasons and making familiar weather patterns alien. Plants that rely on a specific number of sunlight hours to flower or seed might fail, triggering collapses in ecosystems. Animals dependent on migration cues could face starvation if food sources do not align with their life cycles. Human society would need to reimagine calendars, agricultural cycles, and even cultural traditions built around the rhythm of the year. Earth's orbit also shapes the interaction with the moon, and moving Earth closer or farther from the sun would subtly affect lunar tides and orbital resonance. A closer Earth could experience slightly stronger solar gravitational influence on the moon, possibly altering tidal ranges or the stability of Earth's axial tilt over millions of years. The length of the day could change gradually, affecting circadian rhythms for all living organisms. Stronger tides could reshape coastlines, while weaker tides in a distant orbit could disrupt marine ecosystems reliant on the ebb and flow of oceans. The subtle interplay between Earth, Moon, and Sun is a finely tuned system. Shifting the orbit introduces ripple effects across geological and biological timescales. In imagining extreme orbits, it's intriguing to consider the concept of elliptical paths. Earth's current orbit is nearly circular, minimizing seasonal extremes. But if Earth were nudged into a highly elliptical orbit, the distance from the Sun would vary dramatically throughout the year. At perihelion, the planet would scorch, and at aphelion, it would freeze. Life would need to endure wide swings in temperature, and ecosystems would face immense stress. Imagine summers so hot that rivers evaporate and winters so cold that oceans freeze solid near the poles. Such conditions might favor resilient, adaptable species or drive evolution in entirely new directions. Human infrastructure would need to withstand both extremes, requiring advanced materials, energy storage, and environmental controls. The question of atmospheric dynamics in a different orbit opens another realm of possibilities. A hotter Earth closer to the Sun would experience stronger convection currents, generating massive storms with winds far exceeding those of current hurricanes or typhoons. The increased energy input could drive permanent cyclonic systems in equatorial regions, making large swaths of land almost uninhabitable due to relentless weather. Conversely, a colder Earth might experience weaker but persistent storms dominated by snow and ice. Jet streams could shift unpredictably, redistributing heat in ways that would redefine climate zones. Rivers might freeze for longer periods, and deserts could expand in some regions, while ice sheets grow in others, producing a patchwork of extreme environments. Ocean circulation, the lifeblood of global climate, would also be profoundly affected. Warmer waters in a closer orbit would expand, raising sea levels and potentially destabilizing the thermohaline circulation that distributes heat across the globe. Cold Earth scenarios could slow or even halt these currents, causing drastic cooling in some regions while leaving others relatively temperate. Marine ecosystems dependent on stable temperatures and nutrient flows could collapse, threatening fisheries and human food supplies. Even tiny changes in orbit could ripple through oceans over centuries, highlighting the fragility of the balance that sustains life. The biological consequences of a new orbit extend deep into evolution itself. Organisms might evolve entirely new physiological adaptations to cope with altered solar radiation, temperature ranges, or seasonal cycles. Closer to the sun, darker pigmentation or reflective surfaces could dominate plants and animals to mitigate heat and UV damage. In colder orbits, insulation, fat layers, and hibernation behaviors would become more widespread. Life on land and in oceans would be forced to either migrate, adapt, or face extinction. Over millennia, Earth's biodiversity could look dramatically different, potentially favoring hardy, extremophile species over delicate ones. Human civilization, dependent on stable climates and predictable resources, would face unparalleled challenges. Crops engineered for temperate climates might fail entirely, forcing reliance on controlled environments. Cities might need massive insulation or reflective shields to survive heat waves or freezing winters. Energy demand would fluctuate with extreme conditions, and global transportation could be disrupted by weather extremes. Even cultural aspects like holidays tied to seasons, festivals celebrating harvests, or agricultural rituals might lose meaning in a world where seasons are irregular or extreme. Human ingenuity could adapt, but the cost in resources, technology, and lives would be immense. Long-term, a different orbit could influence the geological and tectonic activity of Earth. Heat distribution affects not only climate, but also mantle convection and volcanic activity. A hotter Earth might accelerate tectonic processes, increasing volcanic eruptions and reshaping landscapes. A colder Earth could slow these processes, leading to geological stagnation and affecting the carbon cycle that regulates atmospheric composition. Ice coverage in colder orbits could place additional pressure on tectonic plates, potentially triggering earthquakes and influencing mountain formation. Every aspect of the planet's structure is linked subtly to its orbit around the sun. Speculative possibilities extend even beyond survival. Imagine humans learning to exploit extreme climates for new technologies or resources. A hotter orbit could allow for solar energy harvesting on an unprecedented scale, while a colder orbit might encourage geothermal energy exploitation. Humans might develop entirely new societal structures, organizing around temperature zones or migration patterns dictated by seasonal extremes. Cities might become self-contained ecosystems, blending architecture, agriculture, and energy production to survive a world that has moved from its familiar orbit. Science, engineering, and culture would evolve to meet challenges previously considered impossible. Even the appearance of the cosmos would change. Stars would appear slightly shifted relative to Earth's new orbit, and planets might traverse the sky in unfamiliar patterns. A closer orbit could make Mercury or Venus more prominent in the sky, while a distant orbit might highlight the outer planets. The moon's phases might adjust slightly due to altered angles with the sun, influencing tides and nocturnal illumination. For astronomers, both professional and amateur, the night sky would offer a new canvas of celestial relationships, challenging old assumptions and inspiring new discoveries. Through this thought experiment, the fragility and fortuity of Earth's current orbit becomes strikingly clear. The habitable zone is narrow, and even small deviations can lead to catastrophic changes in climate, life, and civilization. Yet this also demonstrates the adaptability of life and humanity's capacity for innovation. Life on Earth has endured ice ages, asteroid impacts, and mass extinctions. A shift in orbit would test resilience on a planetary scale. Evolution, adaptation, and technology would all converge to meet unprecedented challenges. The lesson is profound. Earth's precise placement in the solar system is not arbitrary. It is the result of billions of years of cosmic chance and delicate gravitational interactions. The planet's orbit ensures the right amount of sunlight, stabilizes climate, supports oceans, and provides predictable seasons. Alter this orbit, and the familiar rhythms of life unravel, revealing just how finely balanced the conditions for life truly are. It's a testament to the intricate choreography of the solar system, where gravity, energy, and motion combine to create a haven for life amidst the cold and empty expanse of space. In the end, imagining Earth in a different orbit is more than an exercise in curiosity. It is a meditation on cosmic balance, the fragility of ecosystems, and the extraordinary luck that allows life to thrive. It invites us to appreciate the precise conditions that sustain us, to marvel at the interconnections between planetary motion and the diversity of life, and to recognize the extraordinary circumstances that have made Earth not just a planet, but a home. To wonder what Earth would be like elsewhere is to glimpse the vast possibilities of the universe, and to understand that our world is, in many ways, a perfect, improbable oasis in the vast cosmic desert. Consider Earth shifting into the inner solar system near the orbit of Venus, or even closer. Here, the sun's intensity would transform the landscape in dramatic ways. Equatorial regions could become uninhabitable, with surface temperatures regularly exceeding 50 to 70 degrees Celsius. Water bodies could evaporate rapidly, creating vast arid zones. The atmosphere itself could change chemically over centuries. Increased heat and evaporation might trigger more frequent and intense storms, while water vapor, a powerful greenhouse gas, could accelerate warming in a feedback loop. Life in such an environment would face unprecedented challenges. Most familiar plants and animals would struggle to survive, and species that do adapt would likely exhibit extreme heat resistance. Organisms might evolve reflective surfaces, heat-dissipating behaviors, or burrowing habits to avoid the scorching sun. Desert-adapted species like cacti or reptiles might dominate, but even they would face limits under such intense solar energy. Humans, in this inner orbit scenario, would face existential challenges. Agriculture would become almost impossible in open fields. Hydroponics, vertical farms, or controlled environment agriculture would be essential for survival. Water scarcity would emerge as a critical issue, requiring innovative desalination, recycling, and storage solutions. Urban life might shift underground, beneath massive protective shields, or even move into artificial floating habitats in cooled water reservoirs. Energy demands would soar, not only to maintain habitable environments, but also to power cooling, air circulation, and water production. Technology and ingenuity could sustain human life, but only at tremendous cost and with careful planning. Moving Earth outward, past Mars and toward the asteroid belt, creates an entirely different set of extremes. The sun's energy diminishes sharply, and surface temperatures could drop below freezing globally. Oceans could partially or even entirely freeze, with glaciers extending to lower latitudes. Atmospheric dynamics would shift, slowing wind and storm systems while altering precipitation patterns. Liquid water would become rare, except near geothermal hotspots or under ice layers, which might act as refuges for life. In this frozen world, species would evolve insulation, anti-freeze proteins, and hibernation strategies to survive the bitter cold. Even humans would face tremendous challenges. Agriculture would have to rely on artificial light and warmth, and energy production would focus on maintaining warmth and supporting essential life-sustaining systems. The length of the year in alternative orbits compounds these challenges. A closer orbit would shorten the year, compressing seasonal cycles and forcing plants and animals to adjust reproductive or migratory behaviors. Many species have evolved to rely on precise seasonal cues for breeding, flowering, or migration. A faster orbit could disrupt these cycles, causing population declines or extinctions. In a distant orbit, a longer year stretches seasonal patterns, potentially leading to prolonged winters or summers that exceed the survival thresholds of many species. Humans would need to redesign agricultural schedules, calendars, and social systems to accommodate these changes. A highly elliptical orbit would introduce even more extremes. At perihelion, the planet could experience temperatures approaching those near Venus, while at aphelion, vast swaths could freeze under sub-zero conditions. Such temperature swings would make survival difficult for most organisms and destabilize ecosystems. Human settlements might need to be mobile or designed to withstand both extremes, relying on advanced materials, insulation, and energy storage. Evolution would favor extremophile species capable of surviving both heat and cold, while delicate species could vanish. Over thousands of generations, life might adapt in ways that are almost unrecognizable compared to today's flora and fauna. Ocean currents would be severely disrupted in alternative orbits. Warmer waters near a closer orbit could expand and destabilize the thermohaline circulation, causing unpredictable heat distribution and extreme weather events. Conversely, colder orbits might slow ocean circulation, creating stagnant regions or persistent ice coverage that affects nutrient distribution. Marine life, finely tuned to current patterns, could face catastrophic disruption. Fisheries would collapse, and human reliance on the oceans for food would necessitate technological intervention, such as artificial aquaculture or nutrient-rich water recycling. The moon's relationship with Earth would also shift. In a closer orbit, stronger solar gravitational effects could subtly change lunar tides and axial tilt stability, potentially shortening days over long timescales. In a distant orbit, weaker solar influence could alter tidal patterns, impacting ocean ecosystems and coastal processes. Tidal energy, which humans might rely on in these scenarios, would fluctuate unpredictably, requiring new designs and technologies to harness it effectively. Climate feedback loops would intensify under new orbital conditions. Closer to the sun, ice caps would melt, increasing ocean volume and accelerating warming. In distant orbits, ice would grow, reflecting sunlight and creating a cooling feedback loop. Atmospheric composition could change over centuries. Greenhouse gases could accumulate or diminish depending on temperature-driven processes, altering heat retention and weather patterns. Cloud formation, precipitation, and storm intensity would all shift, producing climates radically different from those known today. Life itself would evolve under these extreme conditions. Plants in hotter orbits might develop heat-resistant pigments, reduced leaf surfaces to minimize water loss, or deep root systems to access groundwater. Animals could evolve reflective skin, nocturnal lifestyles, or heat-dissipating appendages. In colder orbits, species might grow thicker fur, antifreeze-like blood proteins, and extended hibernation cycles. Biodiversity would likely decrease overall, favoring species capable of surviving extreme energy fluctuations. Over evolutionary timescales, life on Earth might look almost alien compared to the current biosphere. Human culture and society would also transform. Civilizations might cluster in habitable zones, leaving extreme areas sparsely populated or abandoned. Energy infrastructure would dominate societal planning, as warmth, cooling, and resource management become critical. Food systems would rely on controlled environments, perhaps leading to centralized megafarms or vertical agricultural cities. Transportation, trade, and communication networks would adapt to new seasonal patterns and weather extremes. Social organization might become more regional, shaped by climate conditions rather than political boundaries. Geological and tectonic processes could respond to altered climate and temperature regimes. A hotter Earth might accelerate mantle convection, increasing volcanic activity and reshaping landforms. A colder Earth could slow tectonic processes, potentially reducing volcanic activity and stabilizing continents. Ice accumulation in cold orbits could exert pressure on tectonic plates, triggering earthquakes or influencing mountain formation. Over millions of years, the surface of Earth could be fundamentally reshaped by these processes, creating landscapes unlike anything seen today. The night sky itself would be transformed. In a closer orbit, planets like Mercury and Venus would dominate the morning through evening sky, while the moon's phases might appear slightly altered due to changes in perspective and orbital mechanics. In a distant orbit, outer planets like Jupiter, Saturn, or even Uranus might become more prominent, offering new astronomical views. The apparent positions of stars would shift slightly, challenging astronomers and inspiring new interpretations of celestial patterns. Civilizations might develop entirely new systems of navigation and timekeeping based on these altered celestial observations. Exploring Earth in different orbits also highlights the incredible precision of our current position. The habitable zone is narrow, and life depends on a delicate balance of solar energy, orbital stability, and seasonal predictability. Even minor deviations can have cascading effects across climate, ecosystems, and human civilization. This perspective emphasizes the uniqueness of our planet in the solar system and the extraordinary luck that has allowed life to flourish for billions of years. In a philosophical sense, imagining Earth in a new orbit invites reflection on the fragility and resilience of life. It underscores how closely connected life is to the rhythms of the cosmos and how much of existence depends on circumstances that we often take for granted. Humans might adapt technologically to extreme conditions, but natural life forms are more constrained, revealing the intricate interplay between environment and evolution. This thought experiment illuminates the fine margins that define habitability and the extraordinary balance that sustains the diversity of life. Finally, considering alternative orbits reminds us of the broader universe beyond Earth. Planets orbit stars at varying distances, and many worlds exist in extremes far beyond our own. Studying how life might survive in such conditions, on hotter, colder, or more variable planets, helps us understand the possibilities of extraterrestrial life. The exercise of imagining Earth elsewhere provides insight not only into our own planet's delicate balance, but also into the potential diversity of worlds in the cosmos. It sparks curiosity, inspires exploration, and emphasizes the remarkable circumstances that make Earth a cradle for life. Let's imagine Earth pushed to an orbit even closer to Mercury, where the sun's intensity is almost twice what we experience today. The sky would blaze with sunlight, casting a near-permanent glare over the surface. Water would boil more rapidly, rivers might evaporate entirely during the day, and the atmosphere could thicken temporarily with water vapor before being stripped away over millennia by solar winds. Only life forms capable of extreme heat resistance could survive. Plants might evolve reflective surfaces to reduce heat absorption, while animals could burrow deeply underground or develop mechanisms to survive scorching daytime temperatures. Life, if it persisted, would be highly specialized and fragile, surviving only in pockets where shade, water, and insulation coincided. Humans would need to retreat entirely underground or create massive shielded habitats to protect against solar radiation and heat. Even with advanced technology, energy demand for cooling and water production would dominate civilization, potentially limiting population sizes and shaping a very different society from what we know. On the other extreme, Earth drifting toward Jupiter's orbit would create a frozen world, bathed in the weak sunlight of the distant sun. Average global temperatures could plummet below -100 degrees Celsius in some regions. Oceans might freeze entirely, leaving only subsurface liquid water near geothermal hotspots or beneath ice layers. Life would have to be adapted for extreme cold and scarcity of energy. Plants, if any survived, might rely on chemosynthesis near geothermal vents, while animals could evolve antifreeze-like blood, thick insulation, or extreme hibernation cycles. Human civilization would be forced to rely on artificial habitats, energy-intensive indoor agriculture, and geothermal or nuclear energy to maintain livable conditions. Long-term survival in such a distant orbit would likely require a level of technological sophistication far beyond today's capabilities. The potential for elliptical orbits amplifies these extremes. A highly elliptical orbit could create a world that oscillates between scorching heat at perihelion and deadly cold at aphelion. Ecosystems would be subject to extreme stress, favoring only species that can endure wide temperature swings. For humans, survival would demand flexibility, habitats designed to withstand both extremes, energy systems capable of buffering against heat and cold, and food production systems resilient to rapid environmental shifts. Civilizations might develop seasonal migration patterns on a continental scale, moving population centers in rhythm with extreme orbital changes. Oceanic systems would react dramatically to new orbits. Warmer Earth positions would expand oceans, accelerate evaporation, and potentially destabilize currents like the Gulf Stream, producing unpredictable heat distribution and extreme storms. Cold Earth scenarios would slow circulation, creating stagnant, ice-covered seas and severely affecting nutrient distribution. Marine ecosystems, which rely on precise current and temperature patterns, could collapse. Human reliance on oceans for food and trade would be deeply challenged, necessitating advanced aquaculture and synthetic food production. Earth's moon would feel the subtle effects of a shifted orbit. Changes in solar gravitational influence could alter tidal patterns, affecting coastal ecosystems, navigation, and even energy production. Over long timescales, Earth's axial tilt could destabilize slightly, producing erratic seasons and further challenging life adapted to predictable cycles. These changes would ripple across ecosystems, weather patterns, and human societies, highlighting the delicate balance of the Earth-Moon-Sun system. Atmospheric dynamics would also respond to altered solar energy input. In hotter orbits, convection and storm intensity could reach unprecedented levels. Hurricanes, tornadoes, and monsoons could become far stronger, with some regions rendered nearly uninhabitable due to persistent extreme weather. In colder orbits, storms might weaken, but produce persistent snow and ice, slowing water and nutrient cycles essential for life. Feedback loops would amplify both warming and cooling trends, reshaping global climate and further testing the adaptability of life. Plant and animal evolution would reflect these extremes. In hotter orbits, organisms might evolve reflective, heat-resistant exteriors, nocturnal behaviors to avoid daytime heat, and highly efficient water retention systems. In colder orbits, species might develop extreme insulation, fat layers, and anti-freeze-like biological compounds to survive the freeze. Biodiversity could decrease overall, with extremophiles dominating landscapes, while delicate species might vanish entirely. Over millennia, Earth's biosphere could become unrecognizable compared to today, a stark testament to the influence of orbit on life. Human societies would need to restructure entirely. Cities might migrate seasonally to follow habitable zones or develop massive indoor environments with climate control. Food production would shift entirely indoors, possibly relying on artificial sunlight or geothermal energy. Energy infrastructure would dominate societal planning, determining settlement viability. Social systems, cultural practices, and even religious or seasonal traditions would adapt to new orbital conditions, creating civilizations profoundly shaped by planetary placement rather than geography alone. Geological processes would also be affected. A hotter orbit could accelerate mantle convection, increase volcanic activity, and reshape landscapes through erosion and heat-induced crustal stress. A colder orbit might slow tectonic activity, preserve ice sheets, and create pressure on tectonic plates from expanding glaciers, producing earthquakes or influencing mountain formation. Over millions of years, the surface of Earth could be fundamentally reshaped by these new orbital conditions, producing landscapes unlike anything in the current geological record. Even human perception of the cosmos would change. Stars and planets would appear slightly shifted in the sky. The moon's phases might subtly change, and familiar celestial cycles could be disrupted. In inner orbits, Mercury and Venus would dominate morning and evening skies, while distant orbits might highlight Jupiter, Saturn, and Uranus. Civilizations would develop new astronomical frameworks, navigation techniques, and cultural interpretations of the cosmos. Considering Earth in alternative orbits illuminates the extraordinary precision of our current placement. The habitable zone is narrow, and even small deviations produce cascading effects on climate, ecosystems, and civilization. Life has evolved to depend on predictable solar energy, orbital stability, and seasonal patterns. A shift in orbit would disrupt everything from plant reproduction and animal migration to human agriculture, technology, and culture. Yet it also highlights the resilience of life and human ingenuity in adapting to extreme conditions. Philosophically, this thought experiment emphasizes the delicate balance that sustains life. Earth's orbit is a rare confluence of gravitational forces, energy input, and axial stability, creating conditions conducive to life. Imagining a different orbit is a meditation on fragility and chance, on the narrow margins within which life can persist, and on the extraordinary luck that has allowed billions of years of evolution and the rise of human civilization. It is a reminder that Earth is not merely a planet, it is a finely tuned cradle for life, where the interplay of cosmic forces has produced a world uniquely capable of supporting complex ecosystems. Finally, considering alternative orbits connects directly to the broader search for life beyond our solar system. By imagining Earth in extreme conditions, scientists gain insight into what kinds of worlds might host life elsewhere. Hotter, colder, or more variable exoplanets may be capable of sustaining life in forms we cannot yet imagine. Understanding how life on Earth could respond to orbital changes informs astrobiology, planetary science, and the future of humanity's exploration of the cosmos. It underscores both the fragility and adaptability of life, offering a window into the infinite possibilities of worlds across the universe. Ultimately, pondering what if Earth was in another orbit is an invitation to marvel at the extraordinary balance that sustains life, to reflect on the delicate interplay of cosmic forces, and to appreciate the rare and remarkable conditions that make our planet habitable. From the stability of oceans to the rhythm of seasons, from the evolution of ecosystems to the rise of human civilization, Earth's orbit is central to every aspect of life. Changing it even slightly would rewrite history, reshape evolution, and challenge humanity to adapt in ways that stretch imagination and ingenuity. It is both a cautionary tale and a testament to the wonder of the cosmos, a reminder that our home is not merely a planet, but a perfect, improbable oasis in an endless universe.